so I'm going to start by asking you to imagine yourself on Mars. The environment, the people, the terrain, even the atmosphere are totally different. Would you behave the same way you do here? Probably not. But this is essentially what we do to cells when we use them to test new drugs in environments like Petri dishes before we test them in animals or people. Now, we often test new drugs like cancer treatments on human cells in plastic or glass surfaces before we test them in bodies. And the reason that we do that is so that we can evaluate their safety as well as their effectiveness before we test them in real people. But the problem is that devices like Petri dishes aren't able to recreate the complex environment that the cells experience in the body. And just like the environment around us can impact our behavior, the environment around the cells also impacts their behavior. So this is thought to be one of the reasons why so many drugs are failing during clinical trials. And in fact, almost 95% of cancer treatments fail during clinical trials. So my work, as well as the work of some of the other students in my research group, is focused on making new environments, new devices, I guess, for testing cancer treatments that are going to more accurately recreate the conditions that cells experience in the body, and in particular, in cancerous tumors. So, to solve this problem, we should be trying to recreate the environment as best as we can. And so these are some of the aspects that exist in the body that can affect the cell's response to cancer drugs. But they're difficult to make in Petri dishes, I guess. And so in a Petri dish, the cells are going to grow on a two-dimensional flat surface in a single layer. But in many tissues in the body, the cells grow within a three-dimensional matrix where they're surrounded by other cells. And so because of this, in the body there can also be microscale gradients in things like oxygen, nutrients, like even the drug near the blood vessels, and especially this can be especially pronounced in tumors because the blood vessels can be abnormal, so they aren't as regular as they are in the rest of the body. So it's difficult to reproduce this in environments like Petri dishes because Petri dishes are quite big. So you have a microscale environment in the body and you have a millimeter or even bigger environment in something like a Petri dish. So I'm going to try to explain how in my research group we use engineering to make microscale environments like those that can exist in the body to help solve the problem of recreating some of these types of aspects. And so first I want to tell you a little bit about myself. I've always been driven to try to help other people in my research and in my work. And I've really had that as a goal ever since I was in high school. And so when I was in high school, I was initially hesitant to go into engineering because I guess the stereotypical view of engineering, of building cool things like making computers, building cars, building robots, didn't fit into this as well as something like medicine would, for example. But I later learned that there's so many different ways that engineering can actually help people. I've known people who've done engineering degrees and have gone on to medical school, as well as worked on projects to like biomedical engineering, a wide range of projects in biomedical engineering, and things like clean energy research and making fuel cells and stuff like that. And so I chose to do my undergraduate degree in engineering physics. And so I don't know if you know what engineering physics is. I didn't know what engineering physics was. But I guess it's sort of like a combination between, mine was electrical engineering and physics. And so the reason I chose that is so that I could get more theory and get more understanding of the phenomena and the concepts that I was using or applying in engineering. And so things like when I was learning about circuit components in my engineering classes and how to put them together, I was learning about the physics that drives them in my physics classes at the same time. And I really liked that. And so I went on with my research to work in a field called biomeds. And biomeds stands for Biomedical Micro-Electromechanical Systems, which is a mouthful. But it's a field that uses microtechnology and some of the fabrication processes, so the ways that we make computer chips, but applying them to biomedical concepts. Sorry. Biomes, yes. So biomes I thought was really cool and interesting because what these processes, these microfabrication processes that we use to make computer chips, what they allow us to do is to make structures that are actually on the same size scale as the cells themselves. And so that's really good for what I'm trying to do, which is trying to recreate microscale environments in the body. And so the particular area of biomechanics that I work in is called microfluidics. And in microfluidics, we use tiny channels. And so channels that are smaller than a millimeter, and some of them, they're usually about the same size as a human hair. And we flow fluid through these channels to do a variety of different things. And so on the left, that's an example of a microfluidic device. And so the snaking thing that you can see there is the microfluidic channel that you can flow fluid through. And that's to mix fluids. You can have snaking channel like that to mix fluids. On the right, that's another microfluidic channel, and that shows several different colored fluids coming together. And because in a microfluidic channel, the channel is so small, the fluids can actually, they exist in a different regime, so they don't mix when they come together. And so you can actually get those parallel lines that you can see in the right image. So they're separate streams with the different colors of fluids as they come in. And so what my group is doing is we're applying devices like this to try to make environments to grow cells in that are going to more accurately reproduce conditions in the body. So remember I mentioned the difference between growing cells in a flat two-dimensional surface versus in a three-dimensional matrix in the body. And so my group uses microfluidic devices to make spherical beads. And I'll show you, this is the device that we use to make the beads. So we make spherical beads out of a gel material. And in this gel material, the cells can grow in 3D. And so this is the microfluidic device that we use to make the beads. And so this here is a mixture of the gel before it has gelled, so it's a liquid, and it contains the cells. And then coming from these channels here, and you can see it here and here, is the oil. And so the gel stream actually breaks off because of the design of this microfluidic device in the oil, and so it makes these balls. And these balls, or droplets, they gel into beads, and so they become more solid as they go down the length of the channel. And then the cells can proliferate, or they can grow inside this bead in 3D to form a three-dimensional cell culture. And so here I have a comparison between the cells growing inside the beads and the cells growing on a flat surface. And so the circles that you can see around, like this. So these circles are the beads. And this is a group of cells, a cluster of cells that are growing inside. And so the cells, when they are initially put into the bead, are just single cells that are spread out in there. But because they're growing in 3D, they form these ball-like structures, which are called spheroids. Versus in this example, they sort of spread out onto the flat surface instead. They don't grow in all 3 dimensions. And so on the left, these spheroids can actually have microscale gradients, like those that exist in the body. So gradients in things like oxygen, nutrients, and drugs, just like in the body, which can allow us to better recreate the environment in the tumor in those early stages of testing cancer treatments. Now, once we have the beads, we can trap them into another microfluidic device. So you can see labeled the beads here, and then the spheroids, once they've grown to be a bit bigger, there. So the reason spheroids aren't like touching the trapping structures, so these C-shaped things are trapping structures that trap the beads. Spheroids aren't touching because there's actually a bead around there that you just can't see in this microscope image. And then we can feed the cells by supplying things like cancer drugs and nutrients to them with fluid flow through the channel while they're trapped. This type of device can be used to screen cancer treatments because trapping the beads allows us to monitor the growth of the cells over time, so we can image them at multiple time points and look at the same bead as it grows. And it also allows us to supply cancer treatments to the device and expose the cells to different conditions in their environment. So this is where my project comes in. It focuses on controlling and measuring the oxygen levels in these microfluidic environments in order to reproduce the conditions in tumors. Specifically, what I'm trying to create is a condition called hypoxia, which is low oxygen levels that can be caused by abnormal blood vessels in tumors. These abnormal blood vessels can also close and then open again. Sometimes they can do that a few times per hour in cancerous tumors, which exposes the cells to cycles of low and then normal oxygen. And cells that are exposed to these low and cycling oxygen levels can be more aggressive and less treatable. So incorporating these conditions, these low and cycling oxygen levels, into the early stages of testing cancer treatments could help us to better predict the response in the body to the drug. But the problem with incorporating these conditions into something like a petri dish is that the size scales are too big. The gases that we would use to control the oxygen levels are too far away from the cells. Just like it takes you longer to run 10 kilometers than 1 kilometer, it takes the oxygen hours to move millimeters through the liquid in the petri dish. So here, on top of the cells. But in the body, it only takes seconds to move a fraction of a millimeter. So to solve this problem, what I do is I shrink everything back down. I use these tiny microfluidic channels, and they're walls they have walls that are made of a material that the oxygen is able to pass through. So I can have separate channels, and the oxygen can pass between them. And so what I do is I grow the cells in one fluid-filled chamber in the device, which is this one here. And then I have control gases that flow through very close but separate channels. And the oxygen can pass through the walls to move less than half a millimeter to control the oxygen around the cells. And this image shows the three-dimensional view of my device, as well as a cross-section where you can see the cell chamber surrounded by, on all sides, by control gases. And so this slide shows the switching times that we can create in our device. So the plot at the bottom left, this one, shows the oxygen levels measured right at the cells while we switch the oxygen level in the gas channels from 10 to 0% oxygen. And you can see that it changes in less than 10 minutes. And these fast switching times allow us to create complex oxygen profiles like this. And because these switching times are so fast, they are actually compatible with the switching times of a few cycles per hour that have been measured in real tumors. And to get data like these measurements, I also integrate tiny sensors into the microfluidic channels to measure the oxygen levels right at the cells. And the way these sensors work is they're measured by just taking a picture with a microscope, and they emit light that changes color depending on how much oxygen is in the environment around the sensors. So on the left, you can see the sensors at 0% oxygen, they're pretty red, and on the right, 10%, and they're pretty yellow. So here's a microscope image of the sensors actually integrated into the microfluidic device. And so you can see the tracking structures here, and then the sensors. And so these are examples of some of the oxygen profiles that we're able to create in the device. We can create oxygen gradients with higher oxygen levels on one side than the other. So you can see two different examples of this where I use different oxygen control channels. In both of them, I put 10% oxygen in the left channel, and they're different because the left example, I use the top channel as well, and so there's a minimal impact of the high oxygen levels on this side, and a more steady decrease in oxygen on this side. And this video shows some cycling oxygen levels inside the microfluidic device. And these kinds of switching times wouldn't be possible in a petri dish due to those large size scales. So tests like this show that we're able to use the device to create cycling oxygen levels like those that can exist in tumors. Skip the next example because I think I'm out of time. But so, in conclusion, I've tried to give an overview of what I'm trying to do and how engineering and microfluidics can help us to control the microscale environment around the cells in a way that's not possible using standard technology like petri dishes because of the large size scales in those devices. So over the next year, what I'll be working on in my work is using these devices to expose cells to these different oxygen profiles and then track their response both in their behavior and in their response to cancer drugs. And so my group's work is a step towards recreating the actual environment that tumor cells can experience in the body. And the better we can do that, the better chance we have of getting early stage test results that are going to predict the outcome of patients, which could help to speed up the development, hopefully, of new and effective cancer treatments. So that's why we try to do what we do. Thank you.